We are very happy to have Jinzhao from ETH Zurich, and he will tell us about the outer entropy Bartnik-Bray inner mass and the gravitational conjecture. Please, sir.
Okay, thank you, Masamichi. I want to thank first the organizers for having me here. Today I'm going to give a talk about outer entropy. That's something physicists have invented to sort of give a coarse-grained entropy for black holes. And Bartnik-Bray inner mass, so this is really a kind of quasi-local mass that mathematicians have invented. So I'm going to show that these two notions that actually are equivalent to each other. And then we shall see some perhaps interesting implications of this connection. So well, as you see from where I'm from a quantum information theory group in ETH, but this talk will be mostly relativistic. Okay, so let's start. Yes, okay, so right, so let me first give you some background on the outer entropy. This is introduced by Ned Aaron sort of as a coarse-grained entropy proposal for black holes. Roughly speaking, what you want is to hold fixed the exterior region which you can observe and maximize over all possible space-time configuration in the interior region in such a way that you maximize the von Neumann entropy of the total configuration. So so that's sort of a motivation for this coarse-grained entropy, and it is termed the outer entropy in the sense that you fix the outer wedge fixed. So this is roughly the picture of what's going on. In their paper, they consider a particular procedure to put in data into this something called characteristic initial data sets. So this black line is the characteristic initial data set. This data should be, so what you see here is or new. So this part is given. And what you need to do is to add data to complete the whole data set in such a way that you maximize the HRT surface area, which measures the fine-grained entropy. All right, so this is roughly speaking what they do. And the interesting thing is for this mu being a apparent horizon, this proposal shows that it shows that this area of the optimal HRT surface, maximum HRT surface, can be constructed and shown to be equal to the horizon area. So in this sense, they managed to show that the apparent horizon area is in fact, in some sense, a coarse-grained measure of the black hole entropy. So this definition has some interesting properties. For example, because of this optimization here, this has sort of automatically a monotonicity or area laws built into it. If you consider sort of area law along the trapping horizons, sort of foliated by these marginal trap surfaces, the area law is automatically built into the definition. Okay, so this has been generalized to surfaces that is not apparent horizon. This is what they call normal surfaces. That basically you have it's something more general. I will come back to this notion later in some following up works. And it has been pointed out that maybe this definition is also a good candidate for a plausible quasi-local mass. So quasi-local mass is something that is also important in general relativity. All right, so this is Yes.
Can I ask a question?
Sure. Yeah.
I guess, yeah, so I guess my question is in the context of the BNR extensions,
Yes.
I guess because of your background in information theory, can I ask, is there a boundary information theoretic interpretation of the monotonicity of these surfaces? Is that does that map onto some well-known?
Yeah, I think precisely, I don't know, but I think, so something I will also come back to this later is that I think what Engelhardt and Wall achieve here is they sort of turn this very geometric area laws into a sort of data processing inequalities. That's usually how we think of sort of every monotonicity property. But I don't have sort of a specific boundary dual of this quantity in mind. Yeah.
Can I comment briefly?
Yeah, sure. Yeah.
Yeah. So when you think of this as if you think of an apparent horizon inside the black hole, and you think of a sequence of surfaces like this mu, in regions where that apparent horizon is space-like, the resulting outer wedges will be nested inside each other.
Right.
And what that translates into is that as mu moves out, you're holding less and less fixed as you coarse grain. So you maximize the entropy subject to fewer and fewer constraints. And so it must be true that the entropy goes up, the entropy that's defined in the manner on this slide. And that's dual to the area law on such surfaces, which says
exactly. Yes. So yeah, that's sort of what I mean by building to this definition in some sense. But of course, it's for the trapping horizons where you have space-like foliations.
But then doesn't that sound like it's related to like fidelity type definitions using like Ullmann's theorem? Where again, just
so
less
in
fixed.
fact, I will come back to this later. In fact, I will claim that every interesting quantity in quantum information theory that has operational meaning, which satisfies some data processing inequality, can always be written in terms of this kind of form, which we call sort of a variational form. So you have some optimization of a particular quantity up to some constraints. So my view of this, what they do is they sort of turn this area law into a data processing inequality. Yeah, but that's sort of very high level perspective. Yes, I mean in a way that exactly as Raphael just explained. Yeah, but so I will sort of come back to this word data processing inequality later. Right. Okay. So this second part is about quasi-local mass. So this is something motivated by the fact that in general relativity, you can't really have a stress tensor for the gravitational energy. So if you strip out all the matter part, so you consider a vacuum solution of Einstein equation, then the equivalence principle basically tells you that locally you can't feel anything. You can't feel the gravitational field. So that's why, so from a physical perspective, you can't have a stress tensor characterizing the gravitational energy. The best alternative is this notion of quasi-local mass, where you try to, come up with a functional that takes a codimension 2 surface as an input and output a positive number. So that's something the sort of started by physicists like Hawking and Perry thinking about this problem, and nowadays sort of gradually taken over by mathematicians. So the particular one I want to talk about is this idea by Bartnik, who has this idea of, so given so Bartnik had this definition in 89. So in 81, we mathematicians and also Witten have proved the positive math theorem. So Bartnik's idea is to say that if we have a compact space-time domain with sigma, the codimension 2 boundary of the domain, we can define the quasi-local mass called the Bartnik mass as the informant Adian mass over all horizon-free extensions of the given surface. So this is to say, sort of like this is a procedure that is kind of dual to what Arenado defined, you now sort of try to look for, the infinite ADM mass over all possible extensions of your surface. And there's this sort of condition that it should be horizon free, that I will come back to this point later. Okay, so the story is Bray proposed a dual version of the Bartnik mass. So this is the version I'm going to focus on mostly in this talk, because the dual of the Bartnik mass is going to be similar to the outer entropy that we see in the earlier slide. So I apologize for this sort of mixed terminology, because Bray and Bartnik, they use inner and outer, referring to the region you try to optimize over, whereas Arenado, they use inner and outer to refer to the region that you hold fixed. So here you have sort of opposite kind of convention for these names. But what we're going to show is that the inner mass that is sort of dual to the Bartnik mass is the outer entropy that is proposed as a coarse-grained horizon entropy.
Are you going to review the Bartnik mass in a little more detail, or is that it?
Yes, I'm gonna review them in detail.
Okay, then I'll save my question for later. Okay.
Okay. So yes, so I'm just going to give you some terminologies for this. I mean, I think this terminology is most natural for what we're going to discuss. A key difference is I'm going to say less about the expansions, sort of, but sort of focus more on just a basis change. Rather than I will call them mean curvatures. Okay, so let me go through them point by point. So we're going to consider initial data sets like given here. So this first one is the manifold. The second one is the induced metric on it, and the third one is the extrinsic curvature. But rather than think of being induced, you can think of being prescribed, right? We're going to consider codimension 2 closed surface on the manifold on the initial data set. We're going to denote it to be sigma. Okay, so this is the picture, and we're going to call this omega, the interior, and this omega bar, the exterior. And we're gonna assume the dominant energy condition rather than the null energy condition. So this is because, this is not really because we need dominant energy condition for proving the result. It's more like, usually in the mathematical literature, all these notions are defined with initial data set that satisfies DEC. So for safety, I just gonna assume the stronger energy condition. And also, we're going to work in both asymptotically flat and hyperbolic data sets. So we're going to assume the HRT proposal works in both settings. Some terminology here. Whenever I say reminding setting, I mean I have a time symmetric data sets. So I mean this data set has no extrinsic curvature. Okay, so this is the reminder setting, and if this is not zero, sometimes it's called space-time setting. Yes. Okay, so the mean curvature is sort of the notion of characterize how quickly the area changes if you evolve the surface of interest in the direction of the normal, right? So usually we're familiar with these expansions in ingoing and outgoing null directions, but now I'm going to just do a basis change and think about sort of this normal that parallel to the initial data set and the normal that is normal to the whole initial data set. Because it's a codimension 2 surface, you're going to have two normals, right? And we're going to denote the mean curvatures as sort of trace the K restricted to sigma and H correspondingly. And we're going to define this sort of mean curvature vector as, you just take this number and take this basis together. This defines a vector in the normal bundle. And this thing is going to characterize how quickly the area changes if you locally distort them or evolve them along the directions. Okay, so the normal expansions are just related in this way. The term outer minimizing simply means, so when I say sigma is outer minimizing, it simply means sigma is gonna, if you move sigma outside in the exterior direction, sort of in this region, then the area is going to increase. So for any sigma prime enclosing sigma, it has a larger area. So this another term is what the early authors called normal. I here call this mean convex because I think it's really sort of a convexity condition of the surface. So this is just saying that this mean curvature sort of in the tangential mean curvature should dominate over the other one. Or if you translate it into the expansions, it simply says the outgoing expansion theta plus should be positive, whereas the other one should be negative. The ingoing one should be negative. Yeah. So it also includes the marginal cases, which are the marginal trapped cases. Okay, so this is what I mean by mean convex. And if you like, so you can say, whenever it's equivalently, you can say the vector. Sorry, I didn't change the notation here. I mean the mean curvature vector is inward space-like. It's the same thing as saying sigma is mean convex. So last point is that I would say a functional is quasi-local if it only takes data from sigma, right? So on sigma, you can imagine there are some intrinsic data or extrinsic data. So you can take whatever data on sigma. If your function, this is the only function to input, then this function is quasi-local. Okay. So for example, quasi-local mass should be such a quantity that you take whatever data on the surface and output a number, a positive number. Okay, so yes, so I'm going to sort of go into a bit detail of these two main concepts that I'm sort of the main objects of this talk, and then talk about the equivalence and then some implications. All right. So as I just explained, conceptually, outer entropy is sort of a way to do coarse graining, but sort of in some technical details, you really want to use this HRT proposal, sort of, and in this setting in particular, the maximum version of the HRT proposal. So yes, so essentially, you look for the data that is in the interior. You look for the maximum one such that you have the largest HRT area, and you divide by 4GH bar to get the entropy. If you write them out, this is all the details, but you don't need to really care about them. You just need to see that this is really just the maximum part that give you the HRT surface. But the important thing here is, without any condition on sigma, this quantity takes the entire outer edge as input, just by definition. Of course, often we impose some constraints like outer minimizing conditions on sigma so that this quantity can be quasi-localized. I'll come back to this point later, but by definition, this takes the entire exterior region as input, because that's the one you want to fix, right? Okay, so in this sort of long paper of Engelhardt Wall, they also say, there are some technical details about when you sort of glue your piece, when you glue your interior piece to your exterior piece, you should make sure the stitches are smooth, right? So these are the conditions they work out. So roughly speaking, the induced metric on the codimension sigma should match, the expansions should match, and there's something called the twist should also match. Okay, so these I call gluing conditions. Okay, so this all in their paper. Yeah, okay, so a few remarks. Why they impose this gluing condition? This is to ensure that the initial data, the whole initial data set, the constraint equations on the initial data set are well defined at the junction. Okay. Okay, this is a repetition of earlier point. They show that for apparent horizon, you know, of course, the maximizer always exists. They find exactly the HEP surface, and they argue that the particular ellipse system always has a solution. That the HEP surface can always be located. Otherwise, for generic surfaces, in fact, we do not know if the maximizer exists. So by that, what I mean is maybe the supremum is achieved sort of in a sequence of filling data, but it's not actually realized in a particular spacetime. Okay, so yeah, the particular maximizer may not exist. So that is to say, we can't replace here by a max. Okay. Okay, so yes, so this is saying the auto entropy by definition takes the whole wedge of data as input, so it's not really quasi-local by definition, but it can be quasi-localized if you impose extra constraints. So there's something I dubbed sort of EWB null algorithm, sort of acknowledging all the authors that sort of work on this. This is something. This is sort of a way to construct a particular fill-in data that is argued to be optimum for sort of a general setting, but I think it's only proved to be optimum in spherical symmetry or in the setting where you have apparent horizon. Right. So these are the yeah. So this I think it's pretty interesting. So also very sophisticated way of construct the data. All right, so let me also expand more on Bartnik mass. So yes, so the Bartnik mass is intuitively, the point is to seek a minimal mass extension of the initial data without horizons. So why we I think I have a point about why we don't. Okay, so, oh no, so the point of not having horizons here is because you don't want to trivialize the definition. Right? So if you look at the definition here, so on the left-hand side, you take all the data that is relevant on the codimension 2 surface as input, and you look for the sort of the extensions that give you the infimum ADM mass. But if you allow horizons, you can have a situation where it's like a bag of gold. So everything can just get pinched to very small. Then you can make sure the exterior sort of the exterior region to this new horizon has a very little mass. So if you do not impose no horizon condition, this infimum will be 0. So essentially, so you don't want that. So you want something that is not trivial. So Bartnik, the original definition by Bartnik requires the extension should contain no horizons, maybe except for the original one that you glue to. Right. So okay. So yes. So this is the definition, and on the left, this is just to say that all this data will be relevant, but usually in the so-called Riemannian setting, where we have zero extrinsic curvature, we don't have these terms. All you have is just the intrinsic metric and the mean curvature. Okay, so again, why these are here? It's because you want the Einstein equation, sorry, the constraint equation to be satisfied. So you need to make sure when you glue them up, you don't have spikes in sort of delta spikes. Right. Okay. So it's positive by definition, right? Because of the positive math theorem, and it has a monotonicity built in, right? Because I mean, here in this setting, monotonicity simply sort of physically means when you have a larger region, you should have a larger mass, because you should imagine you should think of the mass being positive, at least classically. So that's sort of also advantage of this proposal. The disadvantage is sort of is because it's very hard to analyze. Okay, so yeah, so much, I would say much less is understood in the space-time setting than the Riemannian setting. So the Riemannian setting is sort of the simpler version where you don't have to worry about these extra complications. And yeah, so actually in the literature, there's loads of works on studying this very definition, this very object. But I'm only put here a review article. So if you're interested, you can go check this out. He sort of summarizes, what's the current status of understanding this object. So yes, so another point is similar to the outer entropy. It's important to have inf here because the minimizer don't always exist. And in fact, it's sort of embarrassing that sometimes if you don't put any constraints on this data, you can't even decide if this set is empty or not, right? You can't even decide if you can extend at all, right? So maybe this data is just cannot be isometrically embedded into any valid initial data set. By valid, I mean it should satisfy the constraint equations and the energy condition. Okay, so yeah. Okay, so Bray has a modification in his paper proving the Paris inequality, the Riemannian Paris inequality. What he does is to replace no horizon condition with the outer minimizing condition. So it's a bit subtle what's the difference here, but in fact they're different. So the point is that if you do this replacement, then some analysis is actually much easier. So we now consider this version of Bartnik mass. So really there's not much difference. It's just that in the original Bartnik case, you don't want the extension has any new horizons, but here Bray just demand the area is outer minimizing, the original area you consider. I mean the sigma you consider. Yes,
can you remind us?
Yes.
Sorry, in the original formulation, the word horizon meant event horizon or some kind of apparent horizon?
Yeah, like apparent horizon. Yeah. So let's say
it wasn't physically defined on the slide.
Yes, only defined on the slides. Yes. So yeah, so if it's the Riemannian case, it's just the minimal surfaces. So there's no extra minimal surfaces, or in the space-time setting, no more. So the outermost knots don't get updated. Yes. All right. So so the Paris inequality is one of the sort of Bray's motivation to define a dual mass to the Bartnik mass. This motivation comes from the Paris inequality. So here in this formulation, I sort of think of the Paris inequality as a non-trivial fact or a non-trivial property of any initial data sets that satisfy the Einstein equation. So it says if there is a horizon on this data set, then the mass is larger than the outermost one, right? So this mu here is the apparent horizon, which is the outermost marginally outer trapped surface. And I use this compact notation here, where this sort of this MIRR is the something called the irreducible mass. So really it's just a compact notation, but I guess it also has a physical meaning in the sense that sort of this is if you try to extract energy from the black hole, this is sort of the bound. This bounds how much energy you can extract from the black hole. I mean, essentially because of the Peterson inequality. So this is the formula in asymptotic flat setting, and this is in asymptotic hyperbolic setting. Right. Okay. So if you put in 4 here, the usual dimension 4 case, you just have a familiar square root of area situation. And I guess I didn't put any GH bar, I mean G here. Well, actually, I don't think it's needed. Yes, so yeah, this is precise. Okay, so the Riemannian version of this inequality, that means you don't have K here, is independently proved by Huisken, Uniman, and Bray. So the later Bray's proof is more general in the sense it works for higher dimensions up to 8 dimensions, and it works for sort of disconnected horizons. Whereas this proof is a bit earlier, however, it only works for 4 dimensions. All right, so this therefore motivated by this, Bray defined the dual to the Bartnik mass called the inner mass as using sort of the right-hand side of the Peterson inequality. Okay, so this is similar to how Araneda think about the problem of outer entropy, right? So you try to fill in the optimum data such that you have the largest horizon area inside your fill in. But the slight difference is here, you know, if you recall the HRT proposal, the homologous condition, right? So the surface you consider should be homologous to the boundary. But here is more restricted. It should be homologous to the surface you consider. Right? So in this sense, it's therefore it's a quasi-local definition. Okay. Yeah. So, but I mean, this formula just intuitively speaking, just looking for the largest horizon inside in the interior region, and you know, you can try to fill in all the data as long as they satisfy DEC and matches the Bartnik data on the left-hand side.
Can I ask a question?
Yeah, yeah.
I'm trying to understand I know we corresponded a bit about that, but I didn't fully understand your answer. The difference between why you call this inner mass quasi-local, but I think the outer entropy not. Given that formally it's true, of course, that in the outer entropy you hold fixed the entire exterior of what you call, I guess, capital sigma. But in looking for the optimizing extremal surface, that exterior plays no role. Only the data on sigma itself play a role, unless you want the distinction to be that in one case you allow this extremal surface to cross sigma, and in the other you don't. You require it to be entirely in the inner completion. Is that the distinction you're drawing, or is it something else?
Yes. So the distinction I'm drawing is that just formally, by definition, the outer entropy takes all the exterior data. So it could be that if this Bartnik data is arbitrary, it could be that the outer entropy is well, sorry. So it could be that if the outer wedge data is arbitrary, then it could be that outer entropy is realized not in the inner wedge.
Raphael, I thought we proved, assuming energy conditions, that the maximal HRT surface consistent with a given outer wedge, assuming you have a normal surface, that HRT surface has to lie within the inner wedge.
You mean normal or outer minimizing? I think
yes, assuming outer minimization as well.
Yeah. So this is the point I'm trying to make. So if you don't impose any, so if you think about this outer minimization, it's a global condition, right? It's not you're comparing areas with everything outside. So it's not quantity that you just look at the data locally on sigma, then you can compute. I mean, outer entropy is not such a quantity. But if you know that happens to be outer minimizing and maybe normal, then they match exactly. That's the point of this work. So I'm just saying, if we don't impose any condition on like outer minimizing or normality, then the outer entropy may not be quasi-local. But I agree. I admit this is sort of a bit pedantic to draw the distinction. Yeah. Is it clear?
I'll think some more about it.
Okay. Right. So now this sort of the main object we're going to consider on the quasi-local mass set is the Bartnik-Bray inner mass. Right. So these are sort of quasi-local quantities by definition, and I'm just going to say that it could be that forget about optimizing. It could be that the fill-ins don't always exist. So it could be that there are no fill-ins for a particular set of Bartnik data you choose. For example, this could happen if you have a very large mean curvature, right? So if you have this H number very large, in your data set, then you can't even find a fill-in of your Bartnik data satisfying the dominant energy condition. Okay, so this is sort of a geometric fact that is manifested in the proof of the sort of the positive mass theorem of Brown-York mass. So perhaps I think the Brown-York mass is also used a bit in holography, but in a sort of a global way. Yes. So this is just to say that we can't sort of, if you want sort of physically relevant applications, we can't prescribe Bartnik data arbitrarily. And in this work, we sort of think of the data being induced from a given spacetime. So we know a priori that there's always an extension. So we don't need to worry about sort of this kind of issues. Right. So this is just to say that in the so-called EWB-NR algorithm, so the authors might know this. So of course they know this. So I think in the algorithm, if this quantity is too large, then I think the algorithm cannot output a solution. So this quantity, I mean, the right-hand side is what they use. Of course, for no normal surface, this is a positive number. In this convention, it's sort of just the metric norm of this mean curvature vector. Okay, so this is the point I'm saying. If this H number is too large, you can't find a fill-in. Okay. So another question you might have in mind is that so I don't really restrict anything on the fill-in. So in principle, the fill-in could contain another asymptotic end, right? So you could have a situation where the fill-in and extension together give you something like a double-sided black hole. Just like in Aaron and Lana consideration, they sort of do the CPT reflection of the initial data. You have sort of a CPT symmetric initial data set. So then how are fill-ins different from extensions if they both sort of go out to infinity? The thing is really about the details. So because for the extensions, we care about their ADM mass, right? So if we care about their ADM mass, so they have to have a sufficiently quick fall-off rates. So all the fields should have a sufficiently quick fall-off rate so that the ADM mass is well defined. But for the fill-ins, we don't require this kind of things because we just want there to be a minimal surface or maybe not, but we don't care about how quickly the data fall off at infinity. And also later we're going to impose this mean convex condition, which is the normal condition. This helps to distinguish sort of make a distinguishment between fill-ins and extensions, because convexity is sort of with respect to a normal direction. If you flip the normal direction, it's concave, right? So when we say we consider mean convex surfaces, they sort of make a distinction between the direction of exterior and the direction of interior. Okay, so this is just to clarify, the fill-ins and the extensions are different. All right, so now let's talk about equivalence. So essentially we want to prove this fact for, they are equal, they're equivalent for a auto-minimizing mean convex surface, sigma. I think by now it should be clear that they should match if it's if you put some conditions. So first of all, the gluing conditions all match, right? So if you remember in the Bartnik data, there are sort of 5 entries. The first one being the manifold itself. So really the data is has 4 entries. And also in the EW gluing condition, they also have 4 numbers to match, and they're essentially the same, right? Up to maybe a basis change in the normal bundle, right? Like the sort of, I don't know, relativist convention and I don't know, math convention maybe. But they're essentially the mean curvatures characterize how areas change. Okay, so I'm going to list a few lemmas that are going to be relevant for the proof. So several of these lemmas are already proved by the authors. I believe some are also in the audience. So correct me if I'm wrong. So the idea is that we want to impose auto-minimization because this helps to quasi-localize the outer entropy. Right? So if we know this sigma is in fact the smallest area in the outer wedge, then the HRT surface should locate in the inner wedge. The second lemma is something also sort of apparent from the definition of the inner mass. So remember I said the homology condition is more restrictive in the inner mass case because you want everything to go through sigma, homologous to sigma. Whereas in the HRT case, you just need to be homologous to the boundary. So naturally, because of this constraint, this area, this optimizer, this optimum area, the supremum should be smaller. Okay, so I guess it's also very intuitive. The last one is explains why we need mean convexity or normality. This is because this fact that if you impose this, then the HRT area is always less than the area of the sigma. So if not, if you don't impose this, you could have a situation where this inequality hold in a way that the last two sort of these two this HRT area and the area of sigma swapped, and you can make the area of the sigma sort of very small, but the sort of make the boundary, make sigma close to null. So this area can be very small. Then this area in the middle can help to separate the HRT area and the inner area. I mean, by this I mean that's the supremum area of the inner mass. Then you can't hope to have them being equal. So you have to have this to make sure that they're all smaller than the area of sigma. Okay, so also note, by definition, area of inner should be smaller than area of sigma. Yeah, that's just because that's, you're looking for the minimum surface. Okay, so that's all the lemmas we need. So the idea is, I mean, the proof is really straightforward. You just first, okay, so you suppose those optimizer exist, so you can really draw them in a particular inner wedge that you fill in. Then essentially you should prove by contradiction. You suppose they are not the same, then the HRT optimizer is extremal on some slice n. That doesn't necessarily go through the sigma you consider. So you have this relation because x is the minimal surface on this n slice. The HRT area should be smaller than this y area. Then if you combine some mean convexity and energy condition and the focusing argument, you can sort of show that in this orange data set, this HRT optimizer is also the minimum area surface on this orange slice, right? So then you have a sort of two competing slices for the inner mass. Then by definition the inner mass is the larger one, so you should have the larger area. But the lemma 2 also says it should be the smaller one, so you have equality, right? In the case that if you don't have, I mean, if neither optimizer exists, right? So essentially you don't have a particular space-time that realizes this supremum areas. You can also sort of prove by contradiction, sort of saying that suppose the HRT area, I mean, lemma 2 already tells us that HRT area should be larger or equal to the inner mass area. So by contradiction, you can suppose it's strictly larger. Then there should be some, you can find some epsilon, finite epsilon that interpolates in between them. And this particular AHRT minus epsilon should be realized at some specific fill-in, right? Because if it's not realized at some fill-in, this number should be the supremum. So it's realized somewhere there, then by the above argument, you should have this A inner larger than this particular, essentially the same argument. You should have this situation. But this is true for any epsilon, smaller than the gap between them, right? So you can shrink epsilon to 0. You have continuity. Then this is a contradiction. Okay, so similarly, you can show that it's only going to be both optimizer exists or neither exists. But in any case, the optimal area, the supremum area, is the same. Okay, so yeah, but yeah, okay, so a few remarks. In some sense, these two conditions are really necessary. And here, I put into quote because I didn't prove they are mathematically necessary. I'm just saying that both are needed for this argument. But if we look at how these conditions come from, in the Bartnik case, right, the Bartnik way of thinking this, or the Bray's modification, this is used to avoid the back-of-go-like extensions, right, which will trivialize the bonding mass, right, make 0. So that's why they put this on. But in the EW case, it's sort of, it's sort of their part of their minimal condition, essentially to quasi-localize the outer entropy to make sure the HRT surface is always going to lie inside in the inner wedge. Right. So yeah. So this minimal condition sort of has another piece that making sure their particular construction works. Yeah, but here I'm just saying the same condition is motivated for for completely different reasons. The mean convexity condition is actually quite common in the math world, in geometry analysis in particular. So several positivity of quasi-local mass need this convexity condition, and also you might know this, heard of this Y problem, which is simply saying that the question is whether you can embed a metric on a two-sphere into R3. And the answer is affirmative if you assume the Gaussian curvature is positive, and also the embedding is convex. So embed it as a convex surface. Then there's a unique isometric embedding of any data on R2, on S2 to R3. But sort of, certainly this positivity or convexity is not needed because we can imagine there's an isometric embedded sphere that has sort of a dent on the surface of it, right? But sort of, we don't know any. There's no proof for data on S2 that doesn't impose either intrinsic or extrinsic positivity or curvature positivity conditions. Right? So you need this extra constraint for the proof to work, but it's still open question how the Y problem can be extended to more relaxed constraints. So essentially, the Bartnik problem is similar, right? It can only be more difficult because you essentially want to embed, say, any data on S2 into a data in 3 dimensions that satisfy extra constraints. The Einstein equation give you. So it's mathematically very difficult if you don't impose any convexity constraints, or I don't know, even maybe you need some positive scalar curvature constraints. Okay, so this just to say this is technically easier if you impose this, often in problems. Okay, so yeah, it confirms that the insight by the early authors that realize that outer entropies looks very similar to a quasi-local mass is indeed correct. Okay, so okay, let me come back to the question in the beginning of this talk. So I think one nice sort of conceptual way of looking at this is that the area laws, and I mean the particular area laws with respect to these trapping horizons, space-like fully related, is the same as the monotonicity property of the quasi-local mass. And I think written in this way, they are manifestly sort of a data processing equality. So in quantum information theory, I would claim that all the operationally meaningful quantity we know so far, if they satisfy DPI, they can always be written as variational formulas, right? So, I mean, that's the word, that's why we call them data processing, right? So it should be just as simple as how we see the monotonicity from these definitions. But often, so for example, there's this monotonicity of relative entropy, which is essentially equivalent to the strong subadditivity, they are proved using some different tools in, say, matrix operator algebras, right? They are often not casted in sort of variational formulas. But the point is, you can find a particular sort of hypothesis testing scenario where the monotonicity, where the relative entropy characterizes the ability of hypothesis testing, and then you can write the quantity of interest as a using a variational formula as simple as the area loss, as simple as the Bartnik mass, so that the DPI is actually manifest, right? So I think that's why we don't just call them monotonicity, but data processing equality. Okay, so I think this really motivates the fact that both these objects should have maybe have some boundary dual in a holographic theory, in such a way that we can understand these monotonicities in terms of quantum information quantities. But this is really just a sort of a high-level speculation. Another implication is that since we identify them, and then for quasi-local mass, we should expect that when you shrink it down to a point, when you shrink the surface down to a point, the number should okay, so if it's a good candidate for quasi-local mass, it should reduce to the stress tensor, right? Because otherwise, you shouldn't really trust this as characterizing energy. Yes.
I had a question about like ways to narrow down the specific.
Right. So there's this sort of canonical way of doing this, as I draw here, because it's codimension 2. There's no unique way of narrowing down. So the way of this canonical way is that you choose a time-like vector at any point. Say you're interested in this point, you choose an arbitrary time-like vector, and then you sort of normalize your affine parameter of the light cone on the light cone with respect to this vector. Say you normalize them to be -1, then you take the level sets of the light cone cuts. Right, so these are the light cone cuts. So this is how you shrink it down. And this L here is the affine parameter normalized with respect to E0. Okay.
I'm not sure that, okay, that wasn't the question that I was asking.
Oh, sorry, yes.
So you're saying that this is some speculative thing that has, that you think that there is some boundary information theoretic quantity that corresponds to this thing that obeys a data processing inequality. My question is, if you're trying to determine which boundary information theoretic property is dual to this object, then in some sense, the same argument that you made kind of is somewhat limited in being able to differentiate between different boundary information theoretic quantities, because as you said, essentially any information theoretic quantity you can come up with will obey something like a data processing inequality. So my question is, like, can you use techniques like generalizations of the holographic entanglement entropy techniques to maybe prove additional linear inequalities or things like that must be true about whatever that the boundary information theoretic quantity that this is dual to must obey in order to try to constrain down other properties of whatever the boundary dual of this object needs to be? For example, like, I know this isn't just simple entanglement entropy, but in the context of simple entanglement entropy, you can prove that they need to obey things like strong subadditivity, and some additional inequalities that are true.
Yeah, I'm afraid I can't give any more insightful answers about this question. Basically, I would say I don't understand. The thing is, if you vary over So I think in the holographic dictionary, there's a lack of understanding of the following question. If you prescribe initial data, it's not just the black hole data or vacuum, the usual examples, arbitrary initial data in the bulk, mathematically valid ones, whether there is a boundary dual state to that. And if there is, what are they, right? So I think these are things we don't even understand, but I think they are absolutely needed to answer your question.
Well, I'm not sure I agree, right? I think that you can get started with answering the question by considering spacetimes that you fully understand.
Yes.
And then considering what the geometric definition of the outer entropy gives you in those situations, and considering what in those restricted situations they need to obey or not. Now, these might give you things that are only true for states that have smooth gravity duals, these might give you things that are only true for restricted sets of instances. But in the past, thinking about things like this have allowed people to find more general constraints.
Yes, you're suggesting to apply these ideas to simple spacetime setups so that we understand, right?
Yeah.
Yeah. Okay. Yes. So well, I think yeah. So I think I'll also come back to this. I mean, I think there's some work by people in the Buso group and in your group basically. That's suggesting sort of a boundary dual of, relating the something in the bulk to the co-cycle flow on the boundary. And I think there's something interesting I can say about the connection of, what's going on here, related to that. But I'm afraid if you just apply to a sort of a simple space-time of this procedure, then you don't get much interesting answers, because I will give a couple examples of sort of non-trivial optimizations that one can do in the bulk, that really sort of, it's in the bulk it's slightly, I would say, yeah, it's very different from those examples we understand usually. Just like a structural black hole or ideal black hole with a certain temperature, right? Maybe with perturbations, but I don't think there's a sort of sufficiently non-trivial example to apply these ideas. But yeah, let's discuss more maybe after the talk. Yeah. Okay, so so the second point I'm making is here in the small sphere limit, really the stress entropy, the outer entropy is characterized by the stress tensor. And this, you can confirm this by doing a calculation. Using the algorithm proposed by this author. And the picture you should think of this is like locally at this point, you have light cone, and if you shrink this surface to sufficiently small, closer to the point P, the construction of this algorithm will give you a particular theorem data that has sort of a wormhole neck here, and this area is characterized by the stress tensor here at this point. Okay, so this is how this thing works in picture, and this is the number. And you can see it's for constants, and this is the interesting part, which is stress tensor. All right, so let me come to the implications, the sort of, I think, the more interesting ones. Okay, so I'm going to review this so-called Wall's N conjecture. So so the N conjecture is motivated by the following question. So if an ant that is marching on a sort of a 1+1 dimension spacetime, and she already observed the data, the quantum state on the left of this line, and she wonders what's the sort of energy minimizing state that can have, given her ignorance about the right, region. So if you formulate into equations, you're basically asking what's the informant of the integral of the stress tensor over the right region, over all the purifications of the interior marginal state. And this is yes. Okay, so this is given by, so everyone conjectured to be given by the derivative of the von Neumann entropy of this marginal state, here, and its derivative in this direction. So the right hand side is essentially how the von Neumann entropy changes locally at this point, x naught. Okay, so this is his conjecture, and it's proven for a particular null end marching on a Rindler horizon in arbitrary dimensions. So it's maybe a group of null ends. So this theorem is proved by Sehan Faulkner. It works for any cut on the Rindler horizon with respect to sort of null variations, restricted to the Rindler horizon. So notice the difference here is that on the left-hand side, here we also include the energy of the known piece, right? So this is the piece that the ant already knows about. In particular, she knows about its energy. So you also add this part to the equation in both left-hand side, right-hand side. And because it's on a Rindler horizon, we know there's sort of a general expression due to war that you can write it in terms of the modular Hamiltonian, and they combine nicely into this relative entropy quantity, right? And here is the vacuum state in the reference slot. So the natural question we wonder is, so this is the result in QFT. It's a very general result, but can we imagine something for the gravity sector? So I would say, perhaps trivially, the sort of the equivalence we just established motivates the following conjecture. So first of all, the Penrose inequality suggests the following, right? So if you have a Bartnik mass on the left and this irreducible mass of the outer entropy on the right, because Penrose inequality is about, it's a constraint, or it's a constraint on any data set. So even you have an infimum on the left-hand side and the supremum of the right-hand side, this should still be true, right? And in particular, you can conjecture the following, that because you are taking the infimum on the left and the supremum on the right, the supremum is sort of implicit in the definition here. You can conjecture that under appropriate conditions of the Bartnik data that is given, the following is actually an equality. That is to say, if you fix the interior region and only look for you only vary over the exterior region and look for the energy minimizing configuration, energy minimizing initial data. So it's sort of a similar situation here, right? Okay, maybe it's this one because the total energy, but now it's sort of just a gravitational version, and here the mass is the total mass, the ADM mass, and then on the right hand side we have an entropic quantity in terms of this sort of coarse-grained outer entropy. So in some sense, it's a very natural, it's sort of natural that in the lower bound you have outer entropy, but not any other entropies. It is because in some sense, in the left-hand side, you have a quasi-local mass, right? So quasi-local mass is not really something precise, intuitively speaking. It's more like a compromise because we don't know what's a I mean, it's just forbidden general relativity. But you know, if we believe there's some quantum gravity theory that will eventually supersede general relativity, then there should be sort of a more fundamental physical way of characterize the local energies, you know, better than the quasi-local mass. So in some sense, quasi-local mass is also a coarse-grained quantity, and therefore we should also expect on the right-hand side it is something coarse-grained rather than fine-grained. In the case of the end conjecture, Wall's end conjecture, the left-hand side can be written sort of fine-grainedly as an integral over the stress tensor, and this is something you can't do for the ADM mass, right? So it's sort of natural also in that case that you have a fine-grained entropy that sits at the right-hand side. Okay, so this equation is also purely geometrical, right? So this is something I think, you know, it's just formulated in geometric languages, and one can try to prove it, maybe by impose some extra constraints on the data you have, right? So maybe more than the convexity constraint, you can, you know, impose stronger convexity constraints or some intrinsic curvature constraints to simplify the problem. We know it's actually true in some cases, right? So for example, if we have a surface, if we, you know, take a codimension 2 surface from the Schwarzschild data, then we know the optimal extension and fill-in is the Schwarzschild data, where this where the Pearson inequality is saturated, right? But that's sort of a trivial example. So a good question is, isn't this sort of trivial because you can just, you know, think about whether the Bartnik data that you have is can be isometrically embedded into Schwarzschild data or not. If it can be, then this is true. If it cannot, because of the rigidity of the Pearson inequality, then this is certainly not true. The rigidity of the Pearson inequality says the Pearson inequality is only saturated if and only if it's a Schwarzschild data. Okay, so even this sort of trivial. But I think the subtle point is that it's really important here you have an infimum and a supremum rather than min and max, right? So there's these two sort of non-trivial examples I'm going to sort of briefly discuss. So one is this Mantoudis chain construction of the extension, and another one is Bray's proof of the Riemannian Pearson inequality, where you can see that this equality holds, but you know there's no minimizers, say, on the left-hand side for the optimal solution, right? So this, you can think of this being saying this equality is not true in a particular spacetime, but is true as sort of in the limit of a sequence of spacetimes. So it's important to have the infimum here, and also supremum, I mean, implicit in the outer entropy. Okay, so I would say I would consider this sort of as some, you know, non-trivial evidence for this gravitational end conjecture, so to speak. So let me first mention about this Mantoudis chain construction. So what they do is, you know, essentially, I think of this being the dual version of what Neda and Aaron did for the outer entropy, because, you know, these also consider the parent horizon. Of course, this case is simpler because they consider the Riemannian problem, where you don't have the K0. Okay, but the construction itself is also very it's actually very non-trivial. It sort of give you a particular way doing extensions such that the mass is strictly larger than the horizon irreducible mass, right? So because it's a parent horizon you care about, you can compute its irreducible mass, and these authors is able to construct extensions of mass arbitrarily close to this number, but never exactly equal to this number, right? So this is in the sense that the informant is the informant, which is the body mass, right? The body mass is the informant over all extensions. That informant ADM mass over all extensions is in fact equal to the irreducible mass, which is just the square root of A over 4 pi. But it's never realized in a particular spacetime. And this particular work has been generalized to the hyperbolic data. Another one is slightly different construction, but also interesting, is so-called Bray's conformal flow of metrics. So what Bray wants is to prove the Pearson inequality, and his strategy is to flow the given initial data and flow the metric sort of towards something that is very similar to Schwarzschild. And the flow is given by the following sort of conformal, it has this conformal structure. So you just scale your original metric by a conformal factor. And this conformal factor is 1 in the interior and non-trivial on the exterior. And this, I mean, it has some properties that sort of is exponentially decaying in the far region. I mean, this is going to be also interesting later. And you know, so the interesting fact is, you know, by impose this thing to be a harmonic function, you have a Dirichlet problem, and you can solve it and show that the area under this flow, right, the area of this outermost horizon under this flow is not changing, right? So this area is not changing. So this surface remains outer minimizing, and also the mass of the ADM mass is dropping under this flow. So eventually the ratio of the left-hand side, right-hand side Pearson inequality approaches the Schwarzschild value. But the subtle point is, you know, the limit is never exactly Schwarzschild, right? It's always epsilon close to a Schwarzschild data. So so it's a similar story here. You never actually realize Schwarzschild data in the limit, but you saturate this inequality, you know, in the end of the flow. Okay, so this is also, I consider, an interesting parallel because so there's this proof for the N conjecture by Seyhan Faulkner that I mentioned earlier, where they construct a one-parameter family of purifications, you know, of a fixed marginal state, right? So this is, you know, sort of similar to how Bray constructed a one-parameter family of data that glues to a fixed interior data. And then the mass in this co-cycle flow case exponentially decays to the value predicted by the N conjecture, right? So this is yeah, this is something I get from their paper, and this is sort of also what's happening here. If you have a metric that is exponentially damping in the far region, because the ADM mass is defined using the metric derivative in the far region, the ADM mass is also dropping sort of exponentially towards the optimal value. Here is the Schwarzschild value, right, on the right-hand side of the N conjecture, of the gravitational N conjecture, and here is the sort of derivative of the relative entropy sitting on the right-hand side of the Ward's N conjecture, right? And in both cases, I would say, you know, so the information is not realized at a specific state. Actually, for this one, I'm not very sure, because I think that depends on how generous you want, you know, define a legitimate state, right? So I think there's some works by Busso et al. They show that they end up with a shock at the surface. But I think quantitatively speaking, the situation is similar here. And the sort of question I want to think about more in this scenario is sort of how connected these two proofs of N conjectures are, because on the left-hand side we have sort of a proof of the gravitational N conjecture in a special case, which is Riemannian case, and here we have sort of a proof of Wolf's N conjecture on the null horizon. It's also sort of a special case, and how connected are they? How are they really related in some way? And I mean, there's this very recent work, I mean, also very new, that discusses a plausible bulk dual of the boundary co-cycle flow if you put everything into a holographic setting. And yeah, and I think I haven't fully studied them more, but it's really an interesting possibility to consider. Yeah, and I hope some connections can be made in this direction. All right, so I think the last point I want to make about this is that, so in quantum information theory, a very important tool is the semi-definite programming. It appears everywhere, so this Penrose inequality suggests this inequality, right? And also the gravitational N conjecture is the following. We can think of them being the optimization problems where the informant one is the primal, and the dual optimization problem is obtained by the primal. You're simply swapping the sort of informant and the supremum, and you're swapping the constraints you fix and the objective function you try to optimize. So here on the left-hand side, the primal problem, you have a exterior region to optimize over and an interior region to fix. In the dual, you just swap them. So this is very roughly speaking, how SDP works, how sort of you define the primal SDP and the dual SDP. The interesting thing is, it seems like, because in SDP we have something called weak duality and strong duality. And the inequality is exactly saying the primal should be larger than the dual, and the strong duality is saying the primal should be equal to the dual. Namely, there's no gap between the two optimization problems. And here it seems like it's the same story. But of course, we know that these constraints, they're nonlinear. They're square in the metric, for example, right? There's some for example, the dominant energy condition is square in H. So it's not really a linear problem, but the hope is maybe in the holographic dual, it could be a secretly in SDP. So this is sort of another speculative connection. If we understand how the holography works for this bulk operation. And this is just one last note saying that the gravitational N conjecture itself actually implies the Penrose inequality, right? Because if this is true, then for any other data, it can only be going up on the left-hand side and going down on the right-hand side. So if you assume this without Penrose inequality, then this also implies Penrose inequality. So in the sense, it's a stronger statement. Okay, so let me summarize by proposing some future problems to solve. I think for mathematicians, it's really it will be really interesting if they can somehow prove this statement, because this gravitational N conjecture, as I call it, is actually totally a geometric statement, right? So maybe one can try to first prove it in the Riemannian setting. Also, so can we have a Riemannian version of the algorithm that looks for the field in, right? That is maybe provably optimal for generating enough, not just spherical symmetric Bartnik data. So this, I think, will be interesting to know if they have any ideas. And for physicists, especially holographers, I mean, I have some speculative things to say. I mean, just said just now about you know, what could be the holographic duo of this bulk gravitational and conjecture. And I really want to know whether they are, you know, related in some way. And also maybe a more general question, that's something I always want to understand, is that you know, besides all the, you know, simple examples of duality that we know, is this really you know, legitimate to ask whether any prescribed legitimate bulk initial data, does it have a boundary dual or not? And maybe for this and conjecture, we don't need to understand this general problem, but only these limiting cases, right? We sort of just looking for the optimizers. So maybe in these limiting cases, they can be understood. So, I mean, this is sort of my hope. And in the end, for both mathematicians and physicists, I think it will be really interesting to somehow understand the physical origin of quasi-local mass, right? So this is something that physicists started, but then gradually carried over by mathematicians. Now physicists no longer care about it anymore. But I think, you know, if we believe really general relativity is emergent from some ultimate theory of quantum gravity, then there should be some hints for what are these objects, right? And there are many of proposals, and there are many candidates of quantum gravity. So I'm just wondering whether sort of any quasi-local mass can be understood in any theory of quantum gravity or not. So that's, I guess, my last slide, and thank you very much for your attention.
Thank you, Jinzhao. Does anyone have a question?
Thank you.
Okay, well, I guess if there are no questions, then we should thank Jinzhao again. And
Okay.